Hi, in this video we're going to look at using vectors to solve displacement and velocity questions. Firstly, we're going to look at what velocity and displacement is and compare them to speed and distance. Second, we're going to look at a set of questions that match with the associated worksheet for this video. Those questions will be set into different chapters that you can see in the video, so you can skip forward to whichever question you're having trouble with. So firstly, talking about speed and distance. This is our formula for speed and distance. We have speed equals distance over time. Speed is a scalar quantity. It doesn't have any direction associated with it. We can be going 100 kilometers per hour. That's a speed. We're not saying what the direction is. So in the formula, we've got speed is distance, which again does not have a direction. If I go 100 meters, I'm not saying what direction I'm going in. So it's a scalar quantity. Time also being scalar. If we have a look at our vector equivalent equation, we have velocity being a vector quantity. So it's a speed with direction, equals the displacement. So displacement again is distance with direction divided by time. When you're working with problems in this space, it's really important to know which of these you're working with. So you don't want to confuse this equation with this equation because you'll find yourself in trouble. And it can get a little bit confusing because our displacement uses the same letter as our speed. So it can get a little bit confusing, but that's why it's really important to use proper notation. So notice that our displacement has the underline under it because it's a vector quantity. So it's really important to notate properly in this section, like it is in all sections, but particularly with this so you don't mess up between speed and displacement. Okay, let's move on to some questions. So question 1. A particle moves from point A, which is at 1,3, to point B at -2,6. Determine the displacement vector in component form. So let's draw this to visualize what's going on. We have a point at 1,3, it might be about there. We have a point at -2,6, maybe somewhere up here. We're looking at the particle that's moving from point A to point B. So if we draw that in, we're starting at point A and pointing towards B. So the way to show this using vectors, and there's a few ways you can show this, but using vectors, we can define vectors A and B. So if I draw that in here, coming from the origin, and we often call the origin O, O for origin. So if I was looking at vector OA, that's just going to be 1 across and 3 up. That's going to be -2 across and 6 up. Now if I'm looking at the vector A to B, what we have to do is we have to travel down this way and then travel up this way. So we're going to do negative vector OA plus OB. So AB I'm going to switch these around. So OB is -2,6 minus 1,3, and we end up with -3,3. So our vector is traveling, or our particle is traveling -3 in this direction and then 3 in that direction. So note that with this particular example, this displacement, we've got a distance, which would be the magnitude of this vector, but we also have a direction. We could find a direction of that. We could express it in polar form if we wanted to, where we have a magnitude and a direction. So that's question 1. Question 2. A particle moves 5 kilometers east, then 7 kilometers on a bearing of 330 degrees Determine the displacement vector of the particle in A, component form, and B, polar form. So let's draw this to show what's going on. So we've got a displacement of 5 kilometers east and then 7 kilometers at a bearing of 330. So if I draw another line in here, and we are going 330 degrees, which is going to be up that way for 7 kilometers. Okay, so that's our journey. We're going 5 kilometers east first. Whoops. 5 kilometers, then we're going 7 kilometers this way, where this angle is 30 degrees because it's 330 the whole way around there. So determine where the vector ends up. What we're trying to do is get this vector here. So what is this vector? So to come up with this, we can get our displacement vector for, if we call this A and B, A is going to be 5, 0. B is going to be 7. We need to work out this angle here. That's 120 degrees. So that's 7 cos 120 and 7 sine 120. This green vector is just going to be vector A plus vector B. So all of these units are also in kilometers. Let's not forget that. So if we want, let's call it vector C. Seven cos 120. Cos 120 is negative a half. So we're going to have negative 3.5. Sine 120 is root 3 on 2. So we're going to have 7 root 3 on 2, which equals 1.5, 7 root 3 on 2. Or we could express that as 3 on 2, 7 root 3 on 2. So that's our displacement vector, the one up here in green. That's expressed in component form. Now we need to express it in polar form. So polar form, we need to know the magnitude of C. You can just pop that into your calculator, or you can get 9 on 4. 49 times 3 is 147 on 4. Which is 156 on 4. Now, we can find the surd of that. Let's go through that process. So we got 156. 4 is a factor because 4 goes into 160. So we've got 4 times 39. What goes into 39? I'm not thinking. We got 3 and 13. So they're both prime, so we can't do anything. So that ends up being 4 times 39 on 2, which is equals root 39. Okay, so that's our magnitude of C. Our angle is, let's draw it out. We've got 7 root 3 on 2. I'm not sure exactly what that is. That's about 6. So we've got 1.5 across, and we've got about 6 up. So our angle looks something like that. So theta I'm going to put that into my calculator like this, and you don't need to show this working. But I'm going to put that into my calculator like that so I don't mess up my fractions. And we're going to get 76.10 degrees. Oops. So expressing in polar form, we've got C and we've got our answer to question 2. Question 3. Determine the speed of the velocity vector v equals 815 meters per second. So this is the velocity vector stated in component form. When we're after the speed is the magnitude of the velocity, because velocity is speed and direction. So this is made up of the speed, which is the magnitude, plus the direction if it's given in polar form. So finding the speed, notice that the speed doesn't have an underline under it, meaning that it's a scalar quantity, it's not displacement, equals, I chose these to get an actual integer number, so we get a speed of 17 meters per second. I'm going to show the angle even though the question doesn't ask me, just so you can see what it is. So we have this, we've got 8 across, 15 up, we're after that. Okay, so the velocity has magnitude, it has direction. You might say in sort of layman's terms that I was going 17 meters per second northeast. So that might be a way a person in a physical situation might report that. And again, you could convert that from the positive x-axis to a true bearing or a bearing, whatever your preferred format is, or the preferred format for the question. So that's question 3. Question 4. A particle starts with the position vector OA, I plus 3j meters. The particle moves at constant velocity, v equals negative 5i plus 12j meters per second. Determine the position of the particle after 2 seconds and after t seconds. So let's visualize what's going on here. We've got a starting point of 1 across and 3 up. So starting point here, that's going to be our point A. It's in meters. Then we've got a velocity, which we'll show as a vector, negative 5 and 12 up. So that's our velocity vector. We want to know what the position is after 2 seconds. So we've got our 2 formulas. We've got velocity equals displacement over time. If we're using this, so we want to know what our displacement is for our picture, right? So we got displacement is velocity times time. But we're made up of, you can visualize this as being made up of 2 displacements. We've got a displacement to get us to the original position. Even though it says we start there, we could visualize moving there. And then we're moving to our end spot. So I can say that this is, this is S0. So this is my initial displacement. And this is my next displacement, and I can say S2, which is where I end up, equals S1 plus S0. S1 will just be the velocity 1 times the time plus the starting point as a vector. Our initial velocity was negative 512. and we're timesing that by 2 seconds, plus 1, 3, which is our original displacement. Can do the arithmetic here, so we get negative 10 plus 1, 24 plus 3. Okay, and that's the position we're going to end up in after 2 seconds. If we want to know the position that we end up in after t seconds, we're doing the same thing, except instead of substituting a 2 in here for t, we're substituting a t. So we're going to write that over here. So that's A. Part B is S2. And we get an equation for where we would end up depending on what the time is. So if the time was 2, we would substitute a 2 into each of these t's here, and we would get what we had over here. So that's question 4. I hope you enjoyed the video, and I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.